that we've practiced finding answers of these sets with elements in it, let's practice shading Venn diagrams. So for this first one here, this is the set difference of C and B. I'm going to go ahead and label my Venn diagrams. So what this means is I'm going to start with all of C, and then I've got this whole B's that entire circle. I'm going to erase, get rid of anything that would be in that B circle. So now what I've got shaded in red is that set difference of C and B. Let's look at another one here. I'm going to go ahead and label my Venn diagrams. I'll just do all of them the same way so we don't get really confused. Now, just like what we see with parentheses when we're working out numerical problems, we are going to do the parentheses first. They're the first thing we do in the order of operations, the PEMDAS. Please excuse my dear Aunt Sally, is what some people say. So I'm going to do this parentheses first. So this is the union. So I'm going to shade everything that's in A and everything that's in C in those circles. And again, I want that set difference. So there's my circle B. So that set difference is I'm going to get rid of anything that's in circle B. All right, I want you guys to try C and D. C and D both use our intersection. Remember, to be in the intersection, you have to be in both, in this case, like A and C. So you would have to be in the tiny part that overlaps with A and C. So for instance, the intersection of A and C would be this part here. And I'll show you, because if I think about that whole circle A and that whole circle C, that's the intersection. Both those pieces, it's kind of like two pieces there, are both in A and C. Now I know I said I want you to try it, so I do want you to do that. So go ahead and hit pause and see if you can work C and D. So try to work both of those, and then we'll come back and go over them. So we've got that set difference again. There's my circle B. I'm going to get rid of it. So I'm going to get rid of this little piece. So all I'm left with, oops, I didn't mean to erase it. I wanted to color it in. It's this tiny little piece right there. Now with D, we've got the intersection of A, B, and C, all of them together. So it has to, the part has to be, we're looking for something that's in my A circle, my C circle, and my B circle, in all of them. So there's only one little part that exists in all three circles at the same time. So we've got that little piece right there in the middle. We've got another one here on the next page, and I wanted to look at it, and I'll do it. This is actually something we covered in the last section. That little bar is the complement, or we might say it's not. So it's everything that's not the one we did before. So remember from up here, that intersection. So if I were just doing the bottom part, so don't kind of ignore the line at the top. If I were just doing the bottom part, I'd have this little piece here. That was my answer for D. I want everything that's not that. So I'm going to shade all the pieces that were not in the middle here. So that is my final answer for E. Now let's look at another problem down here that doesn't have to do with those Venn diagrams. This one's a little abstract in our thinking. So if you need to rewatch this, feel free to rewatch it, because sometimes you might need to hear me say it more than one time. So that's totally okay. Like we were talking about right above, this is the intersection. So we can think about the intersection of A, B, and C being this part that we had right up here. So it has to be in A and B and C. It has to be in all of them. So intersections are kind of tiny. If we look up here, they're small. So if we're thinking about the intersection of A and B and C, I'm going to think about that smallest number. And that is 3 up here. A only has 3 elements. So the intersection can't have more than that. C has 10 elements. So you might think, well, why can't it be 10 if I'm thinking the greatest number? If C has 10, there's no way all 10 are in the intersection because only 3 of them can be in A. And you have to be in A, in B, and C to be in the intersection. Now the least number of elements, I know it was back in the last section, but remember we could, well actually I think we did work one up here where we've got the intersection. We could have no elements in the intersection. So that answer would be 0. Intersections I do think smaller because it's only part of the sets. It wasn't all 10 of these items, it was only 3 of them. Intersections I think smaller. For unions, down here, I think larger. Let's see, we've got a union up here in B. So you could, in this one, you don't have to be in the middle. You can be out here floating around on that outside, or not really on the outside, but just in A. So it's not as hard to be in a union. So the greatest number of elements in the union, I could have all the stuff in A, all the stuff in B, and all the stuff in C. So A, B, and C, I could have each one of their unions, each one of their elements. Now the least number is at the very least, I know I have the 10 that are in C. So that is the least amount of elements that I could have in a union, because the union is throwing all of A, all of B, and all of C. So I know if all of C is in there, there has to be 10. There could be more, and that's the case. That's why we have the greatest. If there could be more, we could have each one of them separate. So that's why that union, I think big, is not as hard to be in a union. So I'm thinking those bigger numbers for those answers. Again, feel free to rewind that and listen to those explanations again, or of course, email and reach out as well.